Okay, so get this. You can actually measure gravity
Yeah.
using atoms.
It sounds crazy, right?
It does,
But that's exactly what scientists are doing.
right?
And they're using this wild concept called quantum entanglement to make it even more precise.
I am so fascinated by this.
Me too.
This is going to be a great deep dive.
Yeah.
We're diving deep into a recent experiment
Okay.
from this scientific journal article that really blew my mind.
Uh-huh.
But can we just back up for a second?
Yeah.
Why should we even care about measuring gravity with such extreme precision?
Well, think about it. Gravity is the force that holds us to the planet,
Right.
influences the tides, even affects the way time flows.
Wow.
By measuring it precisely, we can unlock so many secrets about the universe.
Okay.
From understanding how planets and stars form to testing some of Einstein's wildest theories.
Okay, so we're not just talking about some abstract scientific pursuit here.
No, not at all.
This could have some real-world implications.
Imagine being able to predict earthquakes more accurately by detecting subtle shifts in the Earth's gravitational field or discovering hidden underground resources like water or minerals with pinpoint accuracy.
That would be amazing.
More precise gravity measurements could revolutionize everything,
Wow.
from our understanding of the planet to our ability to navigate and explore.
Okay, so let's break this down. How do they even go about measuring gravity using atoms?
It's a technique called atom interferometry,
Okay.
and the basic principle is surprisingly simple. Imagine dropping two pebbles into a pond.
Yeah.
Those pebbles create ripples that spread out and interfere with each other,
Huh.
creating a unique pattern.
I see that all the time at the lake.
Right, exactly.
So how do atoms come into play?
Well, instead of pebbles, scientists use ultra-cold atoms that have been cooled down to nearly absolute zero.
Okay.
These atoms act like one giant wave. We call them Bose-Einstein condensates, or BECs.
BECs.
Okay.
Got it.
Yeah.
What makes them so special for this?
Think of them as the ultimate ripples. Because they're so cold and behave as a single wave, they're incredibly sensitive to any changes in gravity.
Okay.
When those BECs are dropped, their interference pattern changes based on the gravitational field they experience.
So by analyzing that pattern, scientists can actually measure gravity.
Exactly.
That's pretty cool.
It is.
But this experiment takes it a step further by adding in quantum entanglement.
That's where things get really interesting.
Okay.
Entanglement is this bizarre phenomenon where two particles become linked no matter how far apart they are.
Oh, wow.
It's like they're connected by an invisible thread.
Quantum entanglement still makes my head spin a little bit.
I understand that it's a very strange concept.
Yeah.
Can you break it down in a way that I can understand? Imagine you have two coins that are magically linked.
Okay.
Every time you flip them, they always land on the same side,
Okay.
either both heads or both tails.
Yeah.
That's kind of like entanglement. Those atoms are so interconnected that their fates are intertwined.
So it's like a cosmic coin toss where the outcome is always predetermined.
You could say that the
Yeah.
key takeaway is that entanglement actually reduces the uncertainty in the measurements. It's like those linked coins give you a more reliable outcome than if you flipped two regular coins randomly.
Okay, so how do they actually create these entangled atoms and use them to measure gravity in the lab?
Well, first they create this BEC, which is no small feat.
Yeah.
We're talking about lasers and magnetic fields to trap and cool atoms down to a fraction of a degree above absolute zero.
Wow.
Then they use some clever techniques to entangle those atoms. And finally, they release those entangled atoms and measure the gravity based on their interference pattern.
So how well did this actually work?
Well,
Did they get any meaningful results?
yeah, they did.
Yeah.
Even with a relatively small setup, they got within 0.01% of the established value for Earth's gravity.
Wow, that's impressive for a first attempt. It sounds like this whole field of research is really gaining momentum.
Yeah.
But I'm curious, what are some of the challenges in working with these entangled atoms? I mean, quantum mechanics is notoriously tricky, right?
It definitely is one of the biggest challenges, is maintaining entanglement for a long enough time to make those precise measurements you see. Entangled atoms are incredibly sensitive to their environment, even the slightest disturbance.
Okay.
Like a stray magnetic field or a collision with a random air molecule can break that delicate connection.
So it's like trying to balance a house of cards on a windy day.
That's a great analogy.
Yeah.
And just like with that house of cards, researchers are constantly working on ways to shield those entangled atoms from any external interference.
Right.
They use things like vacuum chambers and carefully controlled magnetic fields to create a stable environment where those atoms can do their thing.
It sounds like they're pushing the limits of experimental physics here, but let's step back for a moment and talk about the bigger picture.
Yeah.
Why is gravity such a big deal in physics anyway?
hmm
I mean, we kind of take it for granted in our everyday life.
That's true, but gravity is one of the four fundamental forces of nature,
Yep.
and it's responsible for shaping the universe as we know it. It's what holds galaxies together, governs the orbits of planets, and even affects the way time flows.
Whoa, that's a lot more than just keeping our feet on the ground.
Exactly, and yet gravity is still one of the most mysterious forces. We don't fully understand how it relates to the other fundamental forces, and there are still so many unanswered questions about its true nature.
So by studying gravity with these incredibly precise techniques, are we essentially trying to unravel some of the deepest secrets of the universe?
Absolutely. Think of it this way. For centuries, we've been studying gravity from afar,
Yeah?
observing its effects on planets and stars. But now with atom interferometry, we can actually probe gravity at the atomic level. It's like having a microscope that lets us zoom in and see the fine details of this fundamental force.
That's amazing. But how does this new approach using entangled atoms compare to the traditional methods of measuring gravity?
Well, traditional methods like those used in gravimeters for geophysical surveys rely on measuring the acceleration due to gravity. They're quite accurate, but they have limitations,
Okay.
especially when it comes to sensitivity and spatial resolution.
So are entangled atoms the key to pushing past those limitations?
That's the hope. By using entangled atoms, scientists believe they can achieve even greater precision and sensitivity, allowing them to detect even the tiniest variations in the gravitational field.
Right.
This opens up a whole new realm of possibilities for studying gravity and its effects.
This episode is already blowing my mind, and we haven't even talked about the drop tower experiments yet. Why are they so excited about taking this research to a microgravity environment?
The Einstein elevator, as it's called, is a fantastic facility that allows researchers to simulate microgravity for short periods by conducting experiments in free fall. They can essentially eliminate the effects of Earth's gravity, creating a super clean environment to study the subtle effects of other gravitational forces.
It's like creating a little slice of space right here on Earth.
Exactly.
Yeah.
And in microgravity, those entangled atoms can fall for a longer time without hitting the bottom of the apparatus. This longer freefall time translates to even greater sensitivity in their measurements.
So they're using microgravity to amplify the effects they're trying to measure. That's brilliant. But why go through all this trouble? What's the ultimate goal of studying gravity in microgravity?
One of the key goals is to test one of Einstein's most fundamental principles.
Okay.
The equivalence principle. This principle states that gravitational mass and inertial mass are essentially the same thing.
Wait, so there are different types of mass? I thought mass was just mass.
Well, it gets a bit complicated.
Yeah.
But think of it this way. Inertial mass is a measure of an object's resistance to acceleration,
Okay.
while gravitational mass determines how strongly it's attracted to other objects due to gravity. Einstein's theory predicts that these two types of mass are actually equivalent,
Uh-huh.
but this has never been definitively proven.
So are you saying that by studying gravity in microgravity with these entangled atoms, they could actually test one of the cornerstones of Einstein's theory of relativity?
Exactly. And if they find even the slightest discrepancy, it could revolutionize our understanding of gravity and the universe.
Wow. Talk about high stakes, but it sounds like there's a lot riding on this research. Are there any potential downsides or risks that we should be aware of?
Well, that's a really important question to consider. There are countless potential benefits,
Right.
but we also have to be mindful of how this technology could be misused. Imagine a device that could detect tiny variations in gravity to see through walls or map underground structures without permission.
Wow.
That raises some serious concerns about privacy and security.
It does. It's like something out of a spy movie.
Right.
But couldn't these sensors also be used for good, like helping us find survivors after earthquakes or locate hidden water sources in drought-stricken areas?
Absolutely. The potential for good is immense.
Right.
But like with any powerful tool, we need to establish ethical guidelines and safeguards to make sure it's used responsibly
Yeah,
for the benefit of humanity.
that's a good point. It's a reminder that scientific progress always comes with a responsibility to consider the broader societal implications. But let's shift gears for a moment
Okay.
and talk about the future of this research. What are some of the next steps in developing this technology?
Well, one of the key challenges moving forward is scaling up the experiment. Right now, they're working with a relatively small number of atoms,
Right.
but to achieve even greater sensitivity and resolution, they'll need to figure out how to entangle and control much larger ensembles of atoms.
So it's not just about making it bigger, it's about maintaining that delicate entanglement with thousands or even millions of atoms.
That's exactly right. It's a monumental challenge, but researchers are exploring various approaches, from using different types of atoms that are easier to entangle
Uh-huh.
to developing new techniques for controlling and manipulating those entangled states.
It sounds like there's a lot of exciting work ahead. But what about the practical applications? When might we start seeing this technology being used in real-world scenarios?
Well, some applications, like ultra-precise gravimeters for geophysical research, are already being developed.
Okay.
But as the technology matures and becomes more cost-effective, we can imagine a future where these gravity sensors are integrated into everything from our smartphones to self-driving cars.
Wow.
Yeah.
So we could have super accurate navigation systems that don't rely on GPS satellites or even earthquake early warning systems built right into our homes.
The possibilities are pretty much endless. We're really just scratching the surface of what's possible with this technology.
Wow, we've covered a lot of ground in this deep dive.
We have.
From the bizarre world of quantum entanglement to the mind-boggling implications of measuring gravity with atoms, it's incredible to think that we're now able to probe one of the most fundamental forces of nature at such a precise level.
Yeah, it's a testament to human ingenuity and our relentless pursuit of understanding the universe. Who knows what amazing discoveries and applications await us in the future?
It's a future I'm definitely looking forward to exploring, and we want to hear from you, our listeners. What are your thoughts on this groundbreaking research? What possibilities are you most excited about? Share your comments, and don't forget to like and subscribe to The Deep Dive for more explorations into the fascinating world of science and technology. Until next time, keep exploring.